Okay, good morning, everyone. Welcome to this course. The course is called Markov Chain and Martingales. My name is Hao Wu. My office is just next door. So if you have any question, you can come to my office. Before today's lecture, just a few words about this course. So this course has a three parts. The first part is about discrete time Markov chain. There will be 5 lectures devoted to the first part. So it's from September 1st to October 19th. Second part is about discrete time martingale. There are 4 lectures from October 26th to November 16th. And then part 3 is about continuous time Markov process. So here is the reference for the first part, reference for the second part, and the reference for the third part. I haven't decided yet, but it will be available later. And there will be one final in February next year. Okay, so this is the organization of this course. So the last word is all slides, lecture notes, and the recitation notes will be available on the website of the course. So this is the Sept website, Sept web page under my homepage. So you can find everything there on the web page. So if if you're already familiar with the topic, or you don't want to come to in early Monday morning, you don't need to come, and you can check the slides and the lecture notes and know what is going on during the lecture. Okay, so this is about the courses. Is there any question? Okay, then we can start today's lecture. So today we will introduce, today is an introduction to Markov chain. So there are 7 topics. First, I introduced with the definition to finite state space Markov chain. And then we discussed 2 models of Markov chain. One is called gambler's rune, another one is called coupon collecting. And then we introduced several notions related to Markov chain. It's called irreducible, aperiodic, stationary distribution, time reversal, and random mapping representation. So this is the 7th topic of today's lecture. Another word before of the lecture is, so today there will be 3 classes of lecture. And September 28th, there's also 3 classes of lectures. And the first recitation starts from October 5th, because in the previous, we don't have much exercise to do. Okay, so definition of Markov chain. So in the first part, we start with Markov chain with, so first of all, it is discrete time. Second, it has finite state space. So state space omega is finite. So you can imagine omega is just a finite collection of vertex, and our Markov chain will jumping between this vertex. So omega is finite state space. P is a transition matrix. So it is a matrix. The size of this matrix is n by n. And n is the size of this state space. The definition for Markov chain is, so definition, it is a sequence of random variables such that it has the following property. So this equation says that given what happens after time n, we calculate the conditional probability that what happens to the next step. And this conditional probability equals the transition matrix from xn to xn plus 1. So this is a formal definition for Markov chain. And there are 2 important remarks. First, from this definition, we can see that the conditional probability to jump from one state to another state only depends on these two states. So it is independent of what happens before all these times. So the conditional probability So first remark, the conditional probability to jumping from one state to another state is always pxy. It is independent of what happens before you arrive at x. So this is an important point for Markov chain. A second remark is, from our definition here, we have that the matrix P is a stochastic. So we say a matrix P is a stochastic, which means that we summing over the second coordinate, it always equals 1. So this is also reasonable. It means that once we arrive at vertex x, then all possibility to jumping to other points, the sum is over 1. The sum is 1. So it characterizes all the possibility that we jump to other vertex. Okay, so this is the definition of Markov chain. And then we can go to two examples of Markov chain. The first example is called gambler's ruin. The story is like this. Consider we have a gambler. It's betting on the outcome of a sequence of independent coin tosses. So if the coin is head, he gains $1. If the coin gives a tail, he loses $1. And we require the gambler stops either he reaches the fortune of big N dollar, so this big N is prescribed before the game, or his purse is ever empty, he stops. So this is our story. And this model is called gambler's ruin. And then the natural question is, so here we see that there are two possible fates for this gambler. Either he wins the game, he get N dollars, or he get empty in the end. So the natural question is, what are the possibility of these two possible fates? And the second question is, how long will it take the gambler to arrive at these two possible fates? So this is a story, and this is two questions. And this model, gambler's ruin, in fact, can be modeled by a Markov chain. Okay, gambler's ruin. So how to model this game by a Markov chain? So first, our state space remembers how many dollars the gambler has in his purse. So our state space is an integer number from 0 to n. And x0 is the number of the dollar he has at the beginning. So initial dollar. And then xn remembers how many of the money he has at time n. So money at time n. Okay, so here we can say that in this way we define a sequence of random variables. And for this random variable, there is a special time that is tau. It's the first time he reaches either 0 or n. So in this way, we define a sequence of random variables. Tau is the first time that he stops. And in this model, we see that the state 0 and n are absorbing. So we say these two states are absorbing means once it reaches this state, it will stay there forever. Okay, so this is how to model this story as a mass model. And then our previous two questions is what is the probability for two possible fates? And the second question is how long the time will take. So now if we model this in this way, then our two questions become these two questions. The first question is, so we know that tau is the first time he stops. So this x tau equals either 0 or n. And then our first question becomes, what is the probability of this guy? So this is our first question. And the second question is, how big is this time tau? So this is how we use a math method to model a story. And now we translate the two questions in our math language. Okay, so this is how we model this gambler's theorem by a sequence of random variables. And now we haven't shown that this sequence of random variable is a Markov chain. So how to show it is a Markov chain? So to show it is a Markov chain, the important step is to check this condition. So we want to check what's the conditional probability that if we know what happens after time n, and what's the probability for the next steps. So in this story, it is clear that if we know what happens after time n, we want to calculate what happens to the next step. It only depends what happens at time n. Because at each step, it either lose $1 or gain $1. So what we know is, if we already know at time n, the gambler has k $, then there are only two possibilities for the next step. It is either k plus 1 or k minus 1. And each of them is the probability 1/2. Okay, so in this way we show that this is a Markov chain. And we also give an explicit transition matrix. Okay, to be clear, so suppose our big N is 4. I will write out what is this transition matrix. So transition matrix is the size 5 by 5 because our state space has 5 vertex. And if we start from 0, we know that we will stay at 0 forever. So the probability here is 1. And if we start from 1, we know that 1/2 of the chance we lose $1, and 1/2 of the chance we gain $1. So 1/2. And it's similar here. And finally, if we arrive at the final state, then it stays there forever. So this is the transition matrix for the gambler's theorem when big N equals 4. Okay, so here we see that this gambler's theorem is indeed a Markov chain. And then we can answer the previous two questions. The first question is, what's the probability of this event? So what's the probability that the gambler will win the game? And how long it will take? So how big it is this time tau? So the answer is here. Suppose we start from k $ in purse. So suppose we have k $ in purse at the beginning. Then the answer to the previous two questions is the probability for the gambler to win is k over big N. So before we prove this probability, we can see that this is reasonable. because if we have more dollar at the beginning, we have higher chance to win. And the answer to the second question is, we also know that the expectation of the time is k times n minus k. And this answer is also reasonable because if our k is close to 0, so we will be very quick to reach 0, so the time is shorter. And if our k is close to big N, we will also be very quick to win the game, so the time is also short. Okay, so now how to prove this theorem? So first, how to calculate that probability for the gambler to win a game? So of course we know that this probability should depend on the initial dollar we have in purse. So suppose we denote this probability in this way. So of course, this probability should depend on k. So this pk means we start from k dollar and what's the conditional probability that we win the game. And then let us check what happens. Let us calculate what is probability. So what we do is, let us check what happens at the first step. So we know that we start from k. And what has a possibility for the first step? There are only two possibilities. One is k plus 1 or k minus 1. So 1/2 probability k plus 1 plus k minus 1. So this is what happens to the first step. And then, after we know what happens to the first step, so see, for this probability, we know that x1 equals k plus 1. And we want to calculate what's the probability for the gambler to win a game. So clearly, this conditional probability is actually the same as pk plus 1. Because it's just in the same way as we start from k plus $1 and we want to calculate the conditional probability to win the game. Okay, so here we see what's the relation between pk and pk plus 1 and pk minus 1. And what we also know is if we start from 0, the probability to win the game is 0. And if we start from $n in purse, then we already win the game. The probability is 1. So now what we know is we know the two boundary value of this function, and we know how to jump from one state to its two neighbors. Combining these two, in fact, there exists a unique solution of this function pk, and this unique solution pk equals k over m. Okay, so this is how we calculate the probability that the gambler wins the game. Is there any question? Okay, and then second part, we calculate how long the time it takes for the gambler to stop. So first, second. The conditional expectation of this time, the expectation of this time tau. So of course, again, this expectation also depends on what we start. So we denote this function as mk. So it remembers that we start from k and what's the expectation of this time tau. And the same as before, we study what happens to the first step. So the first step, there are two possibilities. x1 equals k plus 1, or x1 equals k minus 1. And then we check what's this expectation. So it says that x0 equals k, x1 equals k plus 1, and we want to calculate the expectation of this tau. So what's the difference between the case that if we start from k plus 1, we calculate the expectation of time tau. The only difference is we already jump one step. So the only difference is this guy equals mk plus 1, but plus 1, because we already jumped one step. And similar here. Okay, so this is the relation between mk and its two neighbors. And we also know that m0 starts from 0, because if he has no dollar in purse, he stops the game. Or he has $n in purse, then the time tau is also 0. So mn is also 0. And we also know the relation between mk and its two neighbors. So combining these two, we know that there exists only one solution, and this one solution, mk, equals k times m minus k. As stated in the theorem. So here we talk about the first model. It's called gambler's rune. We show that how to model this story by a Markov chain. And then we solve these two questions. First is what's the probability for the two possible fates, and then how long it will take the gambler to stop. Okay, so this is the first model. Is there any question? Okay, the second model is called coupon collecting. So this is the story. A company issues n different types of coupons, and the collector desires a complete set. So this reminds us a game when we played when we were very young. So a company has a product, and they usually put a small piece of toy in the product, and they will want to collect a complete set. But usually it will take a very, very long time. Okay, so this is the story called coupon collecting. A company issues n different types of coupons, and the collector desires a complete set. So the question is, how many coupons must he obtain so that he gets a completed set? And the natural assumption is, of course, we need to assume that each coupon is equally likely to be each of n types. Okay, so this is the story, coupon collecting. And now, how to model this coupon collecting as a Markov chain? So now, our state space remembers how many different types we have in our collection. So the number of types is an integer number from 0 to n. And our x0 is 0, because we start with no coupon at all. And xn is the number of types we have when we get n coupon. So it's the number of types in the first n coupons. So of course, this number of types will be smaller than n. In this way, we define a sequence of random variable. And then the time tau is the first time that we have n types. And it stops. And then our question is, how long will this collector wait until he gets n types? And then it translates to how big is this time tau. So this is how we model this coupon collecting as a Markov chain. Of course, we haven't shown that it is a Markov chain. And then our question becomes, how big is this tau? Okay, so before we answer this question, let us first check this is a Markov chain. So what is the transition matrix for this model? What we need to know is we need to calculate the conditional expectation after time n, and what's the conditional probability for the next step. So of course, no matter what happens to the past, if we know that we have k types at time n, then it uniquely determines what happens to the next step. So it's independent of what happens before. So what happens for the next step? The next step memorize how many different types we have. We already know that at time n we have k types. And what happens to the next step? There are only two possibilities. Either we get a coupon, but this coupon is already fall into the previous k types. So then in this case, the number of types is still k. Or another possibility is at this type, we get a new coupon. And this new coupon gives a new type. And then the number of types will become k plus 1. Okay, and then let us check what's this two probability. In the first case, we know that we already have k different types. And now we get a new coupon. But this new coupon fall into the previous k types we already have. So what's the probability for that? It is k over n. Because we know it is among the k types we already have. And each type is uniformly distributed in this n types. And for the second, so then it is a minus k over n. So we get a new type. So this is the transition matrix for this coupon collecting model. Okay, and to be precise, so if we suppose our n equals 4, and then the transition matrix for this story is so suppose we start from zero type, of course. And then when we get the first coupon, it is the first type. So here is 1. And then suppose we have one type already. Then what happens is it is either we have the same, we have one coupon, but it's the same type as before. So the probability is 1/4. And the probability for a new type is 3/4. And then two type. Three. Four. So this is the transition matrix for the coupon collecting model. And we also show that for this coupon collecting, it is also a Markov chain because we proved this conditional probability. And this is the transition matrix. And now we can answer our question. Okay, the answer to our question is, so we want to calculate how big is this time tau. So now the first answer is the expectation will grow like n time log n. And then we have a preciser answer. So this preciser answer says the time tau is longer than n time log n plus cn, then the probability will be very small. So it says that almost we should have n log n. Okay, and we have a break and we restart at 10.